Hello and welcome friends. In this video we discuss the integrability of the division function. If we have two functions f1 and f2, both are bounded and integrable, then we show that the function f1 divided by f2 is also bounded and integrable. Statement of this theorem: if f1 and f2 are two bounded and integrable over the closed interval a comma b, and there is an additional condition, that means there exists a number epsilon lambda greater than 0 such that f2 of x is greater than equal to lambda for all x belongs to closed interval a comma b, then f1 and f2 is bounded, f1 divided by f2 is bounded and integrable on closed interval a comma b. So first apply the condition of boundedness. f1 and f2 are bounded. f1 comma f2 are bounded on closed interval a comma b. It is a given. Okay, since therefore there exists a number k such that what kind of this number? Mod of f1 of x is less than equal to k, and their lambda is less than equal to f2 of x is less than equal to k, right? Now f1 divided by f2 of x is equal to, by definition this is f1 of x divided by f2 of x, but this is this is equal to f1 of x mod divided by mod f2 of x. This is a modulus value. Now friend, you can see that if we divide a number 10 divided by 5, we get 2. If we divide a number 10 by 2, we get 5. That means in the division we have, whenever we have a smaller number, the division, the quotient is a greater. So instead of this f2 of x, we will take a smaller number. This is a less than equal to f1 of x is less than equal to k, and in the division we take a smaller than any value of f2 of x, that is lambda. That is f1 divided by f2 of x is less than equal to k divided by lambda, and therefore f1 divided by f2 is a bounded function, bounded on closed interval a comma b. So boundedness is completed. Now let us move toward bounded on closed interval a comma b. Okay friends, now if we have, let us take any 2 points of the closed interval a comma b. So first we consider, let partition, suppose we have a partition first p, let p be a partition of the closed interval x0 equal to a, x1, x2 dash dash dash, xn of closed interval a comma b, and let us take the upper bounds supremum and infimum, capital Mi, small mi, semicolon, capital Mi dash comma small mi dash, semicolon, capital Mi double dash comma small mi double dash, be the supremum and infimum of close interval supremum of the function f1 divided by f2, f1 and f2 in the interval xi minus 1 to xi, right? So we are moving toward this because we have the condition, we know that if we upper sum of f1 minus lower sum of f1 is less than epsilon, since f1 and f2 are integrable, so anyhow we arrange the terms of this f1 and f2. If we are able to prove that upper sum of f1 divided by f2 minus lower sum of f1 divided by f2 is less than epsilon, then we can show that the function is integrable, and therefore we take that the upper sum and lower sum. In order to get upper sum and lower sum, we need supremum and infimum. Okay, then you know that this upper sum minus lower sum, let us take f1 divided by f2 of x1 for all, let us call it as a delta xi, then for all x1 comma x2 in delta xi minus f1 divided by f2 of x2. What is this? This is f1 x1 divided by f2 x1 minus f1 x2 divided by f2 x2. Okay, this gives us f1 x1 into f2 x2 minus f1 x2 into f2 x1 divided by f2 x1 into f2 x2. Okay, now see the numerator of this. We need now capital Mi dash minus small mi dash and capital Mi double dash minus small mi double dash. So therefore we arrange this sum, and we need to add some terms here. So this is equal to mod of here f1 x1 f2 x2 minus f1 x2 is needed. We should take common f2 x2 plus f1 x2 f2 x2 minus f1 x2 into f2 x1. This is our numerator, and what is the denominator? Denominator is mod of f2 x1 into f2 x2 modulus. Now from the first two terms we can take f2 x2 common, then this is less than equal to, applying the modulus property, f2 x2 into mod of f1 x1 minus f1 x2 plus, now here what will be the common terms? Mod of f1 x2 mod of here f2 x2 f2 x1 minus f2 x2, right? So this is mod of f2 x1 into f2 x2, right? Then here you can see that apply the greater number, okay, bounds, apply the bounds of this. You can see that this is less than equal to, this is less than equal to, so this is what? Capital Mi minus small mi supremum, and k into capital Mi dash minus small mi dash plus k into capital Mi double dash minus small mi double dash, right? And in the division we take a smaller number, that is lambda, right? Applying the same criteria, this is less than equal to, this is less than equal to lambda square, lambda into lambda square. Now taking summation over all I. So this is upper sum of the function f1 divided by f2 minus lower sum of the function f1 divided by f2 less than equal to k divided by lambda square into upf1 minus lpf1, okay, plus k divided by lambda square upf2 minus lpf2. Now we can use the conditions of integrability of the function f1 and f2. What is given? Since f1 and f2 are integrable over close interval a comma b. Therefore, for epsilon greater than 0, there exists a partition P with norm mu of P less than delta, such that this UPF1 minus LPF1 is less than, look at this, we need here epsilon divided by 2. Here the function is integrable, so this sum can be less than any number. Therefore, we adjust this quantity such that we must get here epsilon by 2, and hence we take it as a epsilon into lambda square divided by 2k, and UPF2 minus LPF2 is less than epsilon lambda square divided by 2k. So this is less than k divided by lambda square into epsilon lambda square divided by 2k plus k divided by lambda square into epsilon lambda square divided by 2k, which is nothing but epsilon by 2 plus epsilon by 2 is equal to epsilon. So upper sum of f1 divided by f2 minus lower sum of f1 divided by f2 is a less than epsilon, and hence the function is an integrable function.